Cool. Welcome to this talk. We're going to chat a little bit about Aurora storage, which is mystic, so we will make it demystified. My name is Tobias Ternström. I run product management for Aurora and RDS. And this is Merle. He runs engineering for Aurora. Hello. And also, I should mention with this talk, it's fairly technical. We'll try to deep dive. And it's a little bit geeky. So some of it is useful for you to know because to do your job and so on. And some things might just only be interesting, just so you know. So it might be a little bit of the looking under the hood and poking around. So in terms of agenda, we're going to look at just what is Amazon Aurora. Very quickly, that's more the marketing thing. Then quick recap. So generally, how do RDBMSs work? Cloud native database architecture. So this is kind of the fundamental architecture of Aurora and especially the storage. Durability at scale and how we achieve that. Durability meaning how do we make sure not to lose your bytes. This is generally an important thing when you build a database. You give us bytes and we try to give them back to you in a speedy fashion. Performance results, and then we'll have some examples. One is on global databases, one is on database cloning, and one is on backtrack. And given the format of the session, we'll try to answer questions at the end. Okay. So first of all, what is Amazon Aurora? Well, it's an enterprise class cloud native database. So it gives you the speed and availability of traditional commercial databases, but with the simplicity and cost effectiveness of open source databases. We have compatibility for MySQL and PostgreSQL, which means if your app works on MySQL 5.6 or 5.7, it works on Amazon Aurora. It's fully compatible. Same thing goes for PostgreSQL. And finally, we provide you a simple pay-as-you-go model for the service. So let's start with a quick recap on database internals. So, and especially on the storage side of relational database and how they work. So this is a quick recap. We've taken an example here of a balanced tree structure where you see we have a root page, intermediate pages, and a leaf level set of pages. And so once you create an index, for example, in a database, you'll get a structure that looks like this. And when you create the index, you have this structure set up in the buffer pool. As you go make modifications in your data, these pages in the buffer pool in memory will get updated. Every so often, a database does something which is generally referred to as a checkpoint, which means we take all of the pages that were changed since last time we did one of these checkpoint thingies, and we write all of those pages down to disk. And the disk thing is important because we need to make sure we keep your data around, right? Now, given that we do this every once in a while, you can ask, why don't you do this immediately? Well, this is generally a problem with databases because once you're going to write to disk, you need to issue an I/O. And generally, disk subsystems can only handle so many I/Os. Okay? So databases, to be able to guarantee durability and consistency, use something that's generally referred to as a do, redo, undo protocol, which is fairly simple. It means that when you do, this means you issue an insert, update, or run a transaction. You take the old state, could be the price of the book was $20, and we make the change, and we then get the new state, so the altered page in memory, and we get a log record. Okay? And the log record is important because that we can use then to redo this later or undo this. So a redo would mean I have the old state and I have the log record, and I merge the two and I get the new state. And we'll see on the next slide why we would need a redo. Undo is, as you can imagine, the opposite. I have the new state. For some reason, I need to back out of the new state into the old state. So I take the new state and I take the log record and I apply the log record and then I get the old state again. So you can always kind of go do it, you can redo it, and you can get out of it with an undo. So let's take a look at why this is important. So here we have a quick recap on how crash recovery works. And so this is generally very important, making sure that if something happens to your system, could be because someone unplugged a server, It could be because, meteorite hit or whatever, and you need to make sure that you get back to a consistent state. So we have two columns here. We have one that contains the pages on durable storage, meaning these pages were the things we had in the buffer pool that we've written down to disk using this checkpoint process I mentioned. And the second column is the log records that were generated that we use for this do, redo, undo protocol. And then you see T here, and that means the time goes down, okay? So let's take one transaction first. So we issue the transaction, and you can see the start and the stop, meaning we began the transaction and we committed the transaction. And when you commit the transaction, that's when the database gives you a note back saying, okay, I've got the transaction, and I won't lose it. Okay, I'll make sure that it's durable. So that's the D in ACID. So once this happened, so the transaction happened, we generated a log record, and we had to write that to disk. Because if I don't have the log record, I can't guarantee that the data is there in case of a crash. We're missing one column, you could argue, which is what is in the buffer pool. So it made the update, it's in the cache on the server. So if you try to read it, you'll see the new state. And it's in the log files, but it's not written to the data files on disk, okay? Then comes transaction T2, which you can see starts a little bit before this checkpoint that we have there. So T2 starts. We have T2's log record generated when T2 commits. So that's written to the log on disk. The pages on durable storage get updated as part of this checkpoint. But given that the checkpoint happened before the commit of T2, the only thing we write to disk in terms of the data files is whatever happened in T1. Okay? So then T3 happens. There's no checkpoint going on, so write that to the durable storage for the log. And then T4 starts, but T4 doesn't finish. Okay? It does not commit. So you have a system failure that happens there, meaning you have a little bit of T4 in the log. Okay? So now, what happens when you restart the system? Well, clearly the data pages on disk are inconsistent, right? Because they contain only T1, but the application got a commit successfully for T2 and T3, right? So T2 and T3 would be lost, right, if we started the system now. So what happens is when you start the system, you go through the log, you find the last checkpoint, and there we see, okay, everything before that we know has been written to durable storage. Everything after has not. So T2, I need to redo, right? I need to go use that redo protocol. So take the old state, apply the log records, get the new state. T3, I have to redo all of T3. And then T4, I need to undo. So you may say now, well, okay, but why do you need to undo T4? Nothing was actually written to disk. It could have been. So checkpoint isn't the only thing that may cause you to write pages to disk. You may also have memory pressures and things like this that go on that say, okay, I can't afford to keep all of this in memory right now. I need to flush some of it out. So some pages may have been written to durable storage, and then I have to go through the undo protocol. Okay, make sense? So what IOs are actually required now for persistence? So the same type of columns here. So we have the log record write. So as soon as a transaction is committed, you need to write the log record to disk and wait for the disk to acknowledge before you can tell the app that it's done, right? Because otherwise we could lose data, end up in inconsistent state. Then MySQL, as an example, here uses something that Merle called torn page protection write or double buffer write. I call it suspenders and belt write, meaning when I write to disk, we have in MySQL 16K pages. But the disk subsystem may very well not work in 16K blocks. So you might be unlucky when you write a page that the system crashes in the middle. Okay? So you write the torn protection write first with your 16K, and then you write to one place, and then you write it again. Okay? So in order to do just this one update, I had to do 3 IOs. Okay? Now, if I have many transactions going on at the same time, databases generally try to group them together to minimize the number of IOs. And generally, that's a big part of how you optimize a database is you try to do things to minimize the amount of IO you have to do, or you buy very fast disks so you can do a lot of IOs. So since Murley spent a lot of time doing storage stuff. He likes this databases are all about I/O. There are other things in a database also, like these query processors and things like this. But I/O is definitely very important. Right. OK, so what about cloud-native database architecture? What could we change from this traditional way of doing things? And this is the way databases generally work. So pick more or less any database that's been around for a while. This is how they're built, with varying optimizations. But this is the general idea.
Thank you, Tobias. So Tobias talked about databases are all about I/O. It is true. There are queries as well. But
not very important.
In this particular case, the key part is if you are changing a single column in a table, you incur few log writes that are happening. But then the size of the page is 16 kilobytes. So there is a lot of I/O inflation that happens. Even if you change a byte or an integer, you end up writing a lot of data. So this is how the traditional database has been operating. And in the database engine itself, you have the query processor, you have transaction process, state management, transaction processing, you have buffer pool, which is the caching, and the logging layer, which is the durability persistence layer. But the key part idea that we had so far is increase the I/O bandwidth, because you have to do all this I/O. Or decrease the number of I/O. As Tobias mentioned, a lot of batching can be done to reduce the number of I/O. But the size of the I/O is going to be still large. So in Aurora, we took a slightly different approach than the traditional approach, where we said, OK, what is the most important part that we cannot avoid? That is the logs. So can we recover the database from the log? And the answer is true. So we consider log as the database. So in this particular example, you can see we have a log stream, and it has all the logs from time 0 to time now. Okay. So let's see if we can recover a page. So any version of a database page can be constructed using this log. And in this particular example, we try to recover a state of a page. I call it the blue page. And all we need is the log record from the time T1 and T5. Essentially, you take the log records, replay it, produce a new version of the page image. So you can imagine that any version of the page, of all the pages, can be recovered if you have the log stream from time 0. So then you might ask, OK, so is this practical? Relying on the log stream, is it practical? Reason is, if you run a database for, say, a year or 2, if you have to recover a page, you have to replay all the logs for the 2 years. It's not practical. So that means that we need to actually do periodical checkpoint. So we come back to the original problem where traditional databases were also dealing with. You have to do checkpoints, right? So how do we actually achieve in Aurora? So if the problem is, if the database itself, database engine, is doing the checkpoint. So essentially, that is the traditional approach where the database was producing the logs. It was also doing the checkpoints periodically. So it was doing a lot more work. What we do is we push down that work to the distributed storage fleet. So a single database is attached to a distributed storage that spans thousands of nodes. So the idea is put the burden into the distributed storage so that thousands of nodes can do this checkpoint periodically. So then if we have that idea, so you can see that you can separate the lifetime between the compute and storage, because compute lifetime is, the node can go down, it can fail, it has to be replaced, and you intentionally might want to save cost, so you can shut it down. You can scale up. You want a bigger instance for doing heavy queries, and in the low period, you can reduce the size of the database instance. But the storage has to be long-lived. So you can see a clear separation between the lifetimes of storage and compute. So we took advantage of this property that exists in the database. So the first property is you can recover any state from logs. The second state is you can separate compute and storage. It need not be tightly coupled. So with these two ideas, we started building the Aurora database, overall the platform. And what we did was we were very lucky that we have all these services in AWS that we could take advantage of. We built a log-structured distributed storage system that is multi-tenant. By multi-tenant, we mean that the database, the storage fleet co-hosts databases, multiple databases from several customers. So we are not dedicating hardware for each database. It is multi-attach. By multi-attach, we mean that a single database cluster can have multiple database nodes, writers and readers attached to the same storage. So you don't have to duplicate the storage to have read scalability and write scalability. So that is multi-attach. And it is purpose-built for databases in the sense that this storage intimately understands the database. It knows about the pages. It knows about the log records. It knows about the page formats of MySQL. It knows the page formats of Postgres. So it knows all of these things, and it is not a traditional block device storage or a blob storage. It is built for databases. And the services that have been listed here are the things that we used. So one of the core design principles that we used for building Aurora storage is that we behaved as any other customer for AWS. We leveraged everything that is out there to showcase that you can also build an enterprise class service on top of AWS. So we used Amazon DynamoDB for our metadata. So all the database metadata in terms of how big it is, how it is spread around, the metadata of how many machines we use, what versions of software that is running, all of that metadata is stored in DynamoDB.
I think it's an important thing to mention there. So some of you may have heard we have this purpose-built database strategy, meaning we have databases that are purpose-built for certain access patterns. So this is a great example where metadata management is a perfect example of using key value store, right? So DynamoDB is the best choice for us to manage metadata. It's a better choice than using Aurora itself because it is a key value problem.
Very good point. You know, we could have spent time building a metadata store, and we would have lost track on building a relational database. So that's what we avoided by letting that particular part of work to be given to DynamoDB. We leverage that capability so that it has scale out, but it doesn't have the relational capability. So we build the relational capability. So we use Amazon EC2 instances. We don't have special hardware. We use I2, I3 instances, which has local NVMe storage. We use Amazon S3 for storing our backups. So the hot storage that we built is on top of I-class instances, and the backup is pushed to S3. So let's dive deep into how I/O flows into storage node. Tobias.
Cool. Thank you. So here we've zoomed into a storage node. So if you look on the right screen here, I'll point a little bit. So the red thing over here, the square, is database instance that runs the actual instance of MySQL or PostgreSQL. And then we have the zoom in on one of the storage nodes. And then this is an example of another buddy storage node. And when you use Aurora, a minimum of 6 of these storage nodes would be used for a database. And to handle each of the segments, which we'll go into a little bit more detail on. But let's take a look at what happens when you actually do an I/O. So first of all, the database instance has gotten to a point where it wants to send a log record. And it sends log records over to the storage node. This is actually where the first difference between Aurora and other databases using the old way of doing things, if you will, that we went through starts. So generally in a relational database, we talked about the fact that, or overall, I/O are expensive. So you want to do, I/Os as infrequently as possible and rather do large I/Os than small I/Os because there's a limit to how many you can do. So generally in a database, you have something called a log buffer. So as things are written, including commits, they get written to a log buffer. And at some point, you write all of this log buffer down to the transaction log or write-ahead log, just to minimize, instead of every time a transaction commits, you have to issue an I/O. So you pile them up, and you write them every once in a while. we don't have that same problem because we do network I/O, which means we can send off log records much, much faster, or much sooner, rather, than a traditional database does. So we also have some sort of buffer, but if you think about it, given that network I/Os are much cheaper for us, we can have a smaller buffer and send these more frequently. So you might have you began a transaction, you inserted a couple of records, and we've already generated the log records and sent them off, versus having to wait for commit. OK, so gets sent over to the storage node, ends up in memory on the storage node. We have to guarantee that we don't lose these log records before we tell the database instance things are fine. So this is now synchronous. Next step is we write these down to the hot log, to the actual durable storage, to the SSD on that storage node. And then we tell the database instance, I got this, this log record. It's fine. And the database instance, by the way, sends this off to 6 storage nodes at the same time. So it's not like it talks to one at a time. It sends it to all 6. And once we have 4 of them saying, I got it, then it knows that it's safe and it can continue. Okay? So this is the only kind of synchronous path. After this, database instance can move forward. Now, the next step is organize records and identify gaps in the log. OK, so we have this checkpointing thing that Merle mentioned also, which means if something happens and we need to do crash recovery, if we need to start from the beginning of time, it will take forever to recover. So we need to, once in a while, generate the pages so that you can just serve that page without replaying. So we put them into this update queue, and then we look and make sure that we have enough log records to we think it makes sense to generate a page, so we don't generate them all the time, and that there are no holes in the log sequence. So the database instance will attach a log sequence number to every log record. So we can just look and see that we have an entire sequence, and then we coalesce a page and write it to the data pages. Now, sorry, I'm on step 5, jumped a little bit ahead. So we have this update queue where we keep track and look for the holes. Then if we find a hole, so we say, oh, I don't have log record 4, I have 3 and 5, but I don't have 4, so I cannot generate the page. And this might be, who knows what happened, I didn't get it. So we have a gossip protocol, so I can ask my buddies, hey, do you have record 4? I don't know why, but Merlin, they implemented this in Spanish, so it says it in Spanish. Hola, ¿qué tal? ¿Cómo está, señor? Can you? This is a joke. Anyways, so it makes sure it has all of the log records. Then, once it has the full sequence and enough so it thinks it makes sense to generate the data page, we generate the data page and write it to disk. Because at some point, the database instance will ask for these these data pages back. If it comes and asks us and the data page isn't coalesced yet, we'll just go and do it then. Okay? So we always have the log stream, can always generate the data page. Then we periodically send off the log records and data pages to S3 so that we can give you point-in-time recovery. So with Aurora, you can say, OK, I want to roll back, or I want to restore a copy of the database from 1 hour ago or 3 days ago. We also use this for snapshots. If you create a manual snapshot, you can keep that around for the lifetime, or for as long as you want to. Currently, we support point-in-time recovery 35 days back, so you can pick any point in time. And then, given that we keep generating these pages, at some point, we know the pages aren't useful anymore for either the master replica or read replicas, so then we can go and garbage collect and remove these pages from the storage node. We still have pages available so we can recover snapshots in S3. And then also every once in a while, we go and look, we go and run checksums on the data pages to make sure that they are healthy. And if we find a problem, we can use that gossip protocol to ask buddies and say, hey, this page seemed to be broken. Can you send me your version of the page? Do you have it? And again, all steps are asynchronous except step 1 and 2. So we have to guarantee that we don't lose the log record, because that's what we need to recover. But everything after 2 is optimizations. OK?
OK. Thank you, Tobias. So the part that Tobias mentioned is about what goes into a single storage node. The data comes in from the database instance, and then it gets durably persisted. So the flow of the data you can think of, there's only two APIs that the storage node serves. The database sends write log records to persist the log records. There is no checkpoints. So then you can ask, what happens if the buffer pool does not have enough memory, or you do a cold start? Where does the page come from? So we satisfy read page. So there is write log records to store the data, read page to retrieve the page. So there are only two APIs that we support. So it became very simple for us to build a distributed storage. So now the question is, we want to support a database which is 64 terabytes and bigger, in which case we cannot put this data into a single box. So we need durability at scale. That's what we are looking at. So let's motivate the problem that happens at scale. So at scale, you have thousands of machines, lots of switches are being used. There are disks that are there, SSDs, devices, storage devices. So any of them can have independent failures that you cannot control. So at any given point, there are some thing that is failing. So how do you handle with failures? You replicate the data. So you have copies of the data so that when things fail, you have other copies that you can use. So one of the common approaches that people take is, OK, let's replicate 3 ways. And in this particular case, we chose 3 availability zones. Let's put 1 copy per availability zone and do a quorum, because at any given point, something is down. So you cannot wait for 3 out of 3. So let's wait for 2 out of 3. So even if a machine goes down permanently, you have 2 copies. So that's a fair idea. So then the question is, what happens if a AZ fails? Right? If a AZ fails, you lose a copy there. So the good part is you have 2 more copies. There are 2 more AZs that are available. Each AZ contains 1 copy. So if your quorum protocol is 2 out of 3, you can still establish quorum. There's no data loss. You can repair it again. So you come to 3 out of 3 again. Right? So that's a fair problem, solution to have. What happens if there is 1 more failure? So AZ down is a rare event. But when it happens, another AZ also has thousands of machines. There could be 1 failure in any AZ at any given point. So that is not that uncommon. So in which case, if you lose another node in a AZ, when a AZ is down, you lose 2 out of 3 copies. That means you lose quorum, you lose data. This is something that you don't want to have for an enterprise class solution. So obviously, we don't use this method. What do we do? So in Aurora, we tolerate AZ plus 1 failure. So we replicate 6 ways with 2 copies per availability zone. So instead of 2 out of 3, we do 4 out of 6. So and we can talk about the same failure scenarios. What happens if a AZ fails? So we lost 2 copies that was present in that particular AZ, but we still have 2 copies in 2 other AZs. So we continue with 4 out of 6 copies. We maintain write availability.
So why do you need 4 for?
4 out of 6. It's funny, you asked this question in the previous session, and I thought it was a complicated question. He asked a very simple question, okay? So 4 out of 6 is getting majority, okay? So, and we can see why it is obvious here, right? If you have AZ plus 1 failure, you end up with 3 copies. So this is a split brain. So you don't know whether those 3 copies are really down. It could be a network partition, and so forth. So the quorum, that's why we do majority. So 4 out of 6 still have 3 copies. There is no data loss. Of course, the database is down. It cannot write because it's waiting for 4 copies to be there. But we can rebuild from the remaining 3.
It was funny because our last talk, we did this. I asked Murli this question, and he looked like, that's a very advanced question. It's a very hard question. I'm like, okay. Because Murli thought I asked, why did we do 4 out of 6? Why didn't we do 3 out of 5? And that's a very interesting question. Do you have a very brief?
Yeah, I can explain why that is interesting, right? See, we could have done, so the natural thing that people do is you do 2 out of 3, The next thing is 5 copies. You can do 3 out of 5. That would be natural.
So you need uneven so you can get
the majority, right? But then, we chose as a design principle that we should have 3 availability zone protection for our database. So that is the design principle we chose. Okay, we could have done, 6 in the same AZ, and then have the same replication factor, but it will tolerate only the failure of a machine or SSD and so forth. What happens if a AZ goes down? So we chose as a design principle that, for any Aurora database, we will have 3 availability zones. So now, if you have 5 copies, then you have an interesting problem of placement and capacity management. Where do you put, the 5th copy? How do you manage it? Obviously, we can solve it, but then the interesting part, what we did was, if you look at the database, there are data pages and log records. This is what the 2 important parts of the database. And the most important part is the pages, because once the log records have been checkpointed into the pages, you don't need the log records. You need the log records only for point-in-time recovery, and that is stored in S3. So when you look at our implementation, we don't use 6 copies of the database pages, because that is too costly, it's unnecessary. But what we do is we do 6 copies of log records. So even though we have 6 copies, we have only 3 copies of the data pages, 6 copies of log records. So saving the size of the log record stream is not a big deal. So we didn't have to go to 3 out of 5. So that is the long answer, which I didn't want to explain at that point. but it is very interesting. Yeah. So thanks for bringing it up, Tobias. Okay, so the question, this clicker, okay, it's working now. So the question is, we support 64 terabyte databases. I already mentioned that you cannot, for the instances that we use in EC2, it doesn't have that much capacity. So you need to segment the storage. The question is, how do we do it, right? So we partition a storage volume. So each database cluster has a storage volume, and we partition that volume into fixed size segments, and we replicate that each segment into 6 ways, and we call it a protection group.
So when you create a new database, how many of these segments, or how many of these protection groups do we create?
Yeah, so the one key part that segmenting also gives us is the fan out of I/O. So the more the number of segments, more the number of protection groups, more I/O fan out you get, more number of SSDs are taking part in the I/O. So you get even a tiny database instance is backed by thousands of machines. So you get the fan out. So we chose to create 16 protection groups. So at any given point, regardless of the size of the database, we don't know how big the size of the database is going to be. So we start with 16, and we also grow by 16 at a time.
So, so a protection group is 6 segments. So it's 16 times 6.
96 segments. So now the question is, how big these segments should be, right? If it is too small, that means that for a big database, you're going to have too many of these segments. So many means some more failures are going to happen, and you have to constantly be working on the failures. If it is too big, repairs take too long. So what is the trade-off, right? So we chose 10 GB as the size of the segment of the protection group. It is replicated 6 ways. And why 10 GB? Because we measured, and we found that we can replicate it faster. So the key insight here is that as a service, we cannot control the failure rate. It happens whenever it happens because of the instance failures and all of that. We cannot control that. We are just a software service there. But what we can control is how fast we can repair. So we chose to optimize on that. So the question is, how do we do repairs? So we use quorum sets. Let me go with an example. So there is a protection group. It has 6 copies, and we put that on 6 machines, A to F. And everything is good, healthy, and this membership information is given to the database node. So whenever a particular page has to be updated in a volume, the database node first looks at it and says, okay, what is the offset of the page within the volume? And it finds the protection group that contains that page, and then it looks at this metadata and says, okay, what are the machines that have this protection group? And this is, and it sends the log records to those machines.
And so, again, another protection group might be on 6 completely different machines.
Yes. It's a multi-tenant, so we just spread it around. Right? We just make sure that we don't put 2 copies of the same protection group on the same node. So we have intelligence there to make sure that a single failure doesn't cause double failure for us. Right? And the quorum is run on top of this metadata. So it waits for 4 out of 6. Right? So we have software which goes and checks whether these machines are up, healthy in terms of the instance state. EC2 gives us information. We also have network pings. We have application level pings, the state, the size of the devices, and all of that health information. And if our software decides that F looks like it's in a suspect state, it might be unhealthy, we don't know, but there is enough signals on that. What we do is we create another quorum, and we are operating on a dual quorum at this point by adding machine G to it and saying that, okay, G, go replicate from the remaining 5. And we have 2 quorum sets, each with 6 non-overlapping, 5 overlapping, and F is being replaced with G, but we don't know yet. So the database is writing to both quorums at the same time. Instead of writing to 6 machines, now it is writing to 7 machines. It is waiting for 4 out of 6 on each quorum. And what that gives us ability is we can drop any quorum at any given point without losing data.
Why don't we just get rid of F immediately and go to this G?
So if you get rid of F, now you're operating at 4 out of 5. And that is essentially weakening the repair set. And adding a G, this gives us flexibility to drop, move forward, or move backwards in a much cleaner way. Right?
Generally, it's a hard problem to know if something is a real problem, like is something really down, or is it some sort of blip?
Right.
And you don't want to take drastic actions if it was just a blip.
Right. So once we have absolute evidence that we don't need to talk to F, we remove that quorum from the quorum set, and then the future quorum is the current quorum now. And we use this technique for hard failures, soft failures, and also rebalancing, heat management. So there are systems that are constantly checking whether the SSDs are at full capacity, whether there are I/O issues, and so forth. So we inject this repair condition for maintenance operations as well. And this is all happening seamlessly. It's a self-healing system, so the database does not show performance problems to the customer workload when things are moving underneath. So that is a core value proposition. Right? So let's look at some performance numbers, Tobias.
Cool. So let's take a look at this I/O business again. So here's an example of a regular MySQL instance with a replica. And you can see these arrows in different colors. The colors have some meaning here. So you can see blue arrows mean it's log records being sent, log I/O. We have bin log for the red arrows doing replication. We have data pages being written, the gray arrows. We have the yellow arrows as the suspenders and belt writes. And then we have metadata for FRM files, these dark blue arrows. You can see on the MySQL side, there's a lot of I/O going on here. And we're writing down also from the instance to EBS, and EBS itself, Elastic Block Store is replicated. So all of these I/Os are getting written all over the place. And you get a great, if you will, inflation of I/O. So here we ran a sysbench run for 30 minutes, and it managed to get through about 780,000 transactions on the machine we had with this setup, again, because you want the protection of 2 machines in case of AC failure. And we did an average of 7.4 I/Os per transaction. So each transaction had to do 7.4 I/Os. If you count the arrows, it kind of makes sense. So let's take a look at Aurora here on the right side. So first of all, you'll notice that we have 2 read replicas here, and we have our storage nodes. And the only thing we see when in the communication here is log records. So it truly is, this log is the database that Merle was talking about before. And then you see there's a little gray arrow down here between the storage node and S3 because we're writing it to S3 for backup. So that's the only type of IOs that have to happen. And because of the fact that we have to do so much less IO, you can see now roughly the same run. So sysbench, same type of machines. We ran for 30 minutes, and you can see we managed to do about 27 million transactions. So about 35 times more than in the previous example, and less than 1 IO per transaction, which is really the big difference here.
Right.
Okay?
The gray arrow is what helps us to do point-in-time restore in a quick fashion. So this is the example I was explaining, that you don't have to replay all the logs from time 0. So periodically we have these pages, so you can take a point in time, look at the pages, and then apply the logs only after that. And we do this restore in a parallel fashion because we have these 10 GB segments that are split and spread. The backup restore is also happening in parallel fashion. So even if you have a 64 terabyte database, we restore within 2 to 3 hours.
Yeah, that's a super important point, that given that each storage node owns its own segment of 10 gigabytes, it just applies log records for that segment, which means you can do this redo in huge parallel fashion, right? So again, the minimum number of protection groups you had is 16. So it's very parallelized when you create kind of an empty Aurora database. So if we take a look here at write and read throughput, comparing Aurora MySQL to regular MySQL, we see a huge difference on the right side. So we see the left 2 arrows are Aurora running MySQL 5.6 and 5.7, and then you have the two columns, running regular MySQL 5.6 and 5.7. And just eyeballing it, you get a sense that the difference is roughly the number of IOs, because of the fact that we've reduced the number of IOs so much. And then on the read side, it's also significantly faster because of the fact that we've optimized a bunch of stuff in MySQL in the Aurora service. So, Merle, why don't you tell us a little bit about global databases?
Global databases. So far, the architecture that we talked about are any region, we use 3 availability zones. We put 2 copies per availability zone, and the data remains within the region. So we launched this global database last year, and let's see how that works. So on the left, you see the primary region. You have the 3 availability zones. In this example, we show that, let me see how this pointer works. Okay, so this is the primary instance, which is the database instance which causes writes to happen. There are 2 replicas that are associated with the same DB cluster. And this is the storage fleet that we talked about. So when the database instance is sending writes, it is sending the writes to the log records that are being generated, are being sent in parallel to the read replicas, to the storage to achieve 4 out of 6 quorum. And we added a new service, internal service that is managed, that is hidden. The customer does not have to manage this part. It's the same fleet as the storage, but the function is replication. So the primary instance also sends the copies of the log records to the replication server. And all these things happen in parallel. So the load on the primary instance is not that much because this replication server behaves like yet another read replica. So now the replication servers send it to the replication agent across region. This is the second region. And from this point onwards, the replication agent is going to behave like a writer. So it gets the streams of data from the original writer, and it is behaving like a writer. So it sends in parallel to the read replicas that you can have. So with global databases, you can do reads on a different region. and then it's being durably persisted on the storage there. The same 4 out of 6 quorum. So we didn't have to make a lot of changes. We had to make very important change in sense of making sure the data continues to flow on WAN. The network within the LAN versus WAN is very different. The latencies, the failure rates, the throughput you get, and so forth. So we spent a lot of time here. And we modified some parts of the protocol so that when there is a failure in WAN, we can pull the data from the storage here and then send it across. So the data, if there is a WAN outage for whatever reason, or we are deploying some software here, or we are deploying some software here, wherever there is a glitch, the continuous flow of data might be interrupted, in which case the data is not lost. It is still cached. It's durably persisted on the storage nodes here. It is getting pulled, and it is being sent here. So when the catch-up happens, this replica is more behind, but then the catch-up happens in a fast fashion that once it is up, you can start doing read queries there. So with this, what we are able to achieve is high throughput. As I mentioned, the replication itself doesn't have a lot of overhead. It just behaves like a read replica. And we are able to sustain high throughput there. So in this particular example, 150,000 writes per second. Here, the writes are statements, SQL statements per second, with negligible performance impact. And we are able to do this with a replica lag of less than a second cross-region. And we have tested this across all the region pairs, and we are able to keep it up with that. So within US, from the East Coast to the West Coast, we are able to do it less than 100 millisecond, 150 millisecond. And across all the region pairs, we're able to do less than a second. And the important part is, if you choose to promote that, what we call the mirror, into its own DB cluster, you can. And it's a simple operation. It's for us, because the recovery happens in parallel, and the data is already durably persisted, and you can start writing to that mirror. So you can promote a mirror to its own database cluster in less than a minute. Let's look at the performance between logical replication and physical replication. So MySQL has this protocol called as binlog protocol, which is logical. It captures the statements or changes to the rows, and binlog protocol can pull the data from one region to another, and we have a managed binlog replication for Aurora MySQL. And in this particular case, you can see that this is the query per second, and this is the lag. When we reach around 30,000 QPS, the lag starts building up. It's not able to keep up, because it has to logically pull the data from the database engine and replay it. And the writer is doing a lot more work. It is storing the data multiple times, the physical data and the logical data, and it is serving it. In case of physical replication, we're able to achieve 200,000 writes. Still, the lag is less than a second.
And notice that those two y-axes don't have the same scale.
Yes. So this is 500 seconds, and this is the value you see in the physical replication. So the key part is database is all about I/O, right? And the less the I/O, better the performance.
Can you imagine if you have him and query optimizer people in the same room?
Okay, let's see an example. It's US West to US East. We spent a lot of time explaining how the data flows. These are all the redo log records that are flowing. One part to notice is this is a DB cluster of its own right, and it has the backup that is happening here. So you can actually take snapshots and point-in-time restore and so forth on the mirror region as well. So if you want to create an application where you want to do read scalability and also do some analytics or scale out your application, you can do that very easily.
But do we replicate old backups over?
So we do the backup and restore using the same data that is flowing.
But if I created this one and then I created the replica a year later, the global database a year later, do I have the
so
snap?
okay, that's a very good question. So the global database is attached and created at the point of creation of the database. So it doesn't copy all the historical data from one region to another region, but it carries over the data from the point it was created. So in this example, so these two query windows, we are querying the US West, the writer, and the timestamp is highlighted here. And then at the same time, we are doing the reads on the reader and the US East, and the lag is this. So this is not the system. We have CloudWatch metrics. This is not the CloudWatch metric. It's the query from the database itself, and the schema is capturing the timestamp. And you can see that it is keeping up with that. Let's go through cloning.
Thank you. Actually, I wanted to mention one more thing, not related to global database, but just look at this picture. So, or actually not that picture. This one. So one thing we didn't mention, my bad. So we see these log records are flowing also to the readable secondaries. And you may wonder why, because the readable secondaries are obviously reading from the same storage nodes when it needs data. So why would you need to send log records to the read replicas as well? Well, they also have a buffer pool, right? So if they have data in the buffer pool, they need the log records to make sure that that buffer pool is updated, right? And so when it gets the log record, if the data is not in the buffer pool, it can just ignore it, doesn't need it. Because then it would read the page from storage when it needed it. But if it does have something in the buffer pool, it needs to update the buffer pool. So database cloning, this is a nifty feature. So given that we have this central storage layer, and you can create read replicas, you can create up to 15 read replicas. On the global database secondary side, you can create up to 16 read replicas there, and you could promote one to be a master in case of an emergency, so disaster recovery type of thing. Yeah, there was one more thing I wanted to just mention on global database, which is, so Merle mentioned that this replication kind of happens behind the scenes. All you say is, I want a secondary region over here. You don't actually have to have read instances on the other side.
That's right.
Right? So if you want it purely for a disaster recovery, you don't want to read from it, you just want the belt suspenders thing, you can just pay for the storage on that side and not pay for any compute until disaster strikes, and then you create an instance on top of it and can use it. So that's worth noting. So database clone is basically say, hey, I want a copy of this database that I can actually write to. So when you create a clone, we immediately give you a new compute instance with exactly the same storage that the original has, but it doesn't continue, it doesn't get any updates, and it's writable. So this is super useful because it's very fast, and I'll explain why. It's very fast to create, and you can use it either to stamp out new databases. So if you get a new customer and the customer needs a new instance, maybe you have a template instance, you create a clone, and you go from there. Or you use it for testing or things like this. So how does it work? Well, so here we have a source database and a clone database. So when I create the clone, it has exactly the same storage as its source. So when we create it, we don't actually copy any data. The only thing we really do is we do some metadata work and whatnot, and then we create a new instance and point to the same data. And then it's really a fork. So if something changes on the source database, we do copy on write. So we add the changes and keep track of them for the source database. And if there are any writes on the target, then we keep track of those. So we can see here in this case, the source database had the darker blue pages from the beginning. Then it made some updates. So page 2 and page 5. So page 2 was updated. 1 through 4 was the original. So page 2 was updated, and it added page 5. Then the clone, who also had the same blue from the beginning, it still has the original blue, too, because that didn't change on that side. It updated page 3, so it has a new version of page 3. And it also created a new page 5, which is not the same page 5 as the other one, right? And it added its own page 6. So as it diverges, it needs to store more data. But anything that's the same, the union between them, is the same storage. And that's also the storage that you actually pay for. So if we take a look at an example here, so here we inserted 40 million rows, not exactly 40 million rows. As you can see, it's approximately 40 million rows. And it generated approximately 25 gigabytes. Why do I think it's so funny with 40 million? You will see. So you go and click your instance, say I want to create a clone of the data of the instance. So then you look here. There. It's hard to see for you, I know, but it's not exactly 40 million. It's 999,996. So it's almost. There are 4 rows missing. I'm very upset with Merle for these 4 rows. I don't know. Do you also have OCD? It hurts me somehow. But you can see it only uses about 100 megabytes of space, although it has exactly the same contents. And then if we go and update, so we updated about also roughly 10 million rows. At least it doesn't print out many here. So now it's up to 1.2 gigabytes. So you're now paying, in this case, if nothing happened to the source, you're paying for 26.2 gigabytes of storage. So it's a very, very useful thing, and it's very fast to create these clones for obvious reasons, since it's not the size of data operation. Right. So the key part about all these features is that performance is the key. So when and I/O.
And I/O. You get performance because of doing less I/O.
Only query optimization, again, not very bad.
Right. So the important thing that we see from customers is that because clone is fast, because the performance is fast, people change the way applications are being built. So in case of clone, in a couple of minutes, you get a new copy of your database. And in many cases, customers want to get access to the production database, and they don't want their test team or the analytics team to get access to the production account, in which case the clone can be done cross-account. So you give access to your analytics team, and you can clone into their account. And they get access to their production data, which is usually the biggest problem in terms of testing, because you're not representative, the test is not representative. So you test something, but then when you go to production, you have application problems. Or you want to do analytics, and you want the latest data, and you don't want to impact your production OLTP.
And since it's writable, you can create a clone, and then you could run some script to anonymize the data and so on before you run certain tests.
Yeah. So what we have seen is, customers having multi-terabytes of sized database, and then when you clone, it is very less. You can do the analytics, and then you can delete the clone and do a clone again. So you create a new type of workflow. The way you create application itself changes because of the performance.
And you could create a clone on a secondary region as well, and then you could, for example, create the indexes you needed on that side for your analytics workload.
Right. And there are no limits on number of clones you can create. You can just create clone of a clone of a clone, and you can fork, and then you can create a clone. So as time progresses, your production database, if you want to test a new software, you can clone, test it, and if it works well, you can logically copy the data, and then that becomes your production, and you can keep doing it. So it's very powerful. So that's what the storage feature enabled. So let's talk about backtrack. In case of backtrack, so the key idea is how do we quickly recover from unintentional problems, or you want to experiment with the schema, for example. So in this case, the timeline is going left to right, and the database state is shown here. So at time t1 to time t2, so the database went till time t2, and at that time, say, you dropped a table, you dropped a bunch of rows by mistake, something bad happened, and you want to rewind the database to time t1. So what we do is, because the storage knows about the database pages and log records, we maintain a lot of copies of the pages, different versions, and the log records between them. We quickly rewind the storage to point to time t1. We still have the data stored. We just make it invisible to the database engine. So all we do is we blow the buffer pool out, and we restart the engine as of that point in time on the storage. So we're not doing a point in time restore, so the data doesn't come from S3 and we don't create a new volume. Just this volume is quickly rewound. We just make that data invisible. So now you get this new state from T2, go to T3, then say you go to T4, and you do the same thing. We still, again, we make it invisible. So you can see that we are sort of creating a tree of the log space. So we are essentially creating a tree of log sequence numbers, and we are masking certain regions of the logs and making the database to mount a particular point of the volume and quickly bring the database up. And all these operations happen less than 10 seconds. So the backtrack is very quick. So if you have an unintentional issue in your production, you're not down for long. You just rewind and then you do it.
But what if I rewind to the wrong place?
You can go back and forth, and there's no limits on number of times you can do. So you can go, when you go back and forth, essentially we are finding which branch of the LSN tree we want to fall into, and you can do that. And the total amount of backtrack window is something that you configure. And today we allow up to 72 hours of backtrack window.
And it does add a little bit more storage, as you can imagine, so it adds some cost to you in terms of storage.
Right. And this is quite useful if you want to play with your schemas. So today, database schema change is a big deal, so you need to plan for it and so forth. Here, you can just clone your production database, enable backtrack, make changes to your schema, and if you don't like the schema, you can go backtrack and then make another change. So you can quickly iterate how your schema is going to behave. So this is yet another thing, how the performance changes how you build applications. Let's look at an example. So in this case,
so it's a lot faster to rewind than to do alter table, drop column, for example.
Right. And even if the database is in an inconsistent state, you can backtrack. So even if there is a community bug of MySQL or Postgres that you run into, you can backtrack your way out of it. So that's the cool part. So the database does not have to be up to be backtracked. So in this particular case, at 7:05, the table contains 10,000 rows. We are showing 5 rows. No, it's exactly 10,000.
But then why do you have the wave thing?
Right. Because I'm going to show you. Right? So now we created a new column, C1, but we don't show it, but it's there. But we added 2 rows to it, 100,001 and 100,002, and you see the top 5 rows here. And assume that this is a bad operation that you did. That's a oops moment, and say, okay. But the time is 7:09 at this point. So you go to the console, click backtrack on your database cluster, choose 7:06. That was the state that you wanted. Go back. So the console shows that it is backtracking. And then once the database is back up, within 10 seconds, you do the select star, you see the 5 rows again. So that is backtrack. The technology that we built in terms of clone and backtrack is all the same technology. So we have the ability to maintain multiple versions of pages on the storage node that is used to build clone, that is used for backup. So when we take page backups, by the time you copy the data of pages into S3, the pages changes. So we need to do ref counting and copy and write and so forth. So the same technology is what allowed us to build backup, clone, and backtrack. References. So we also wrote in great detail about how this system works. We have a couple of papers, Sigmod 2017 and 2018. I highly recommend you guys to check this out. That's it. Thank you.
Thank you.